Hey guys, it's Mr. Gelsdorf. Wanted to check in with you to do a week one review. So what I'm going to try to do is kind of give you guys lessons at the beginning of the week, and then by the end of the week, do a video where I just kind of go over the details of it and review all the information about it and everything, and then we can continue to ask questions as needed. Okay. So for right now, I am going to be reviewing the Introduction to Equilibrium Notes, or Section 1. And then I'm going to talk a little bit about the dynamic equilibrium packet. And then I'm going to do a tiny bit of section 2. So if you want to pause and go ahead and get these three out, that would be great. So we can go over those. You good? Okay, cool. So in section 1, we learned about what equilibrium really is. So equilibrium, even though it is referring to something being equal, it is not saying that the amount of the reactants and the amount of the products have to be equal. It is saying that the rate at which they are changing is equal. So if one is going up by a value of 10, the other one is going down by a value of 10. And then, changing back at that same rate and then changing back at that same rate. It seems confusing, but when you think about it, it's basically just saying it gets to a point where everything settles out. So the changes stop. You end up with a specific amount of the reactants, a specific amount of the products. And a lot of you probably saw when you are graphing them that the lines kind of come out like this. And so what that is saying is, notice that, this sign would be concentration, bracket. Oh, that's not a bracket. Oh, good. Okay. All right. This is concentration. And notice that they don't end at the same concentration. They don't have to be the same. If they ended at the exact same line, well, then that means that they are the same concentrations. But that's not what equilibrium is. Equilibrium means we get to the point where it just stops changing. The concentrations remain constant after a certain amount of time. So the time at which they became constant, this would be when... That is a messy line. This would be the point where equilibrium's reached, okay? So a big point of information there, and I noticed some of you when you were submitting your dynamic equilibrium packets, I noticed that error, and I know some of you may not have submitted them yet, and that's okay, but I noticed that error on the last question on the back, and then on one or two questions in the middle of the packet. So again, it's about their rates getting equal. So it's almost like if you think about, let's think about a mall, right? And you open the mall, which, I mean, not right now, but you get the idea. You open a mall, and at the beginning of the day, the escalator going up is full of people. So everyone going into the mall at the beginning of the day, because there's no one inside, and everyone's outside. At a certain point, the amount of people going in and the amount of people coming out are the same, roughly. Right? At a certain point, it's kind of a one in, one out sort of situation. So the escalators going up into the mall are going to be about equal. That would be the point where it reaches equilibrium. Now, that doesn't mean that the entire world outside the mall and the number of people inside the mall are the same. We know that's not true. But the equilibrium is the state where it gets to that point where it's going back and forth. Okay? All right. So that's kind of the major point for the first section. The other point being that one thing we may have noticed, and we're going to get to this, and this was one of those questions on the dynamic equilibrium packet I told you weren't supposed to do, my bad. But if a forward reaction is going, then the reactants are going to go down in concentration because they're being used up, and the products are going to go up, right? If it's a reverse reaction, it's the exact opposite. Now, what was I going to say? Oh, so the amounts in which these are going down are going to be the same based on the balanced equation. We'll get to that in another section, but I just wanted you to get the idea that, if the reactants go down by a power of 10, the products are going to go up by a power of 10. So it's always going to be the exact opposite, essentially. All right, so let's get into section 2. In section 2, we introduce the idea of equilibrium position and equilibrium constant. So the position of equilibrium is basically saying... So for instance, the mall example. So in the mall example, the number of people inside the mall is significantly less than the number of people outside the mall. Even if it reaches equilibrium and the same number of people are going in and out, the total quantity of people is different inside and outside the mall. Yes, I'm wearing a Pokemon shirt. Deal with it. So the equilibrium position in that case would be essentially shifted to the side of the world, or the side of the reactants, or whichever side you would wish to identify that as. But the outside world is where the equilibrium position for that is. Now, could all of those people outside go into that mall? Physically, maybe no, but theoretically, yes. So the position can change a little bit, but that means that the constant for that particular reaction is probably on the side of saying, you know what, no matter what, there's always going to be more people outside than there are inside. Okay. I'm noticing this video is lagging a little bit, so if it's lagging on your side, I apologize. I can't fix that, but I'm almost done. Anyways. So the equilibrium position is basically where are you right now? So based on the current position or the current conditions around the reaction, where is the equilibrium right now? The constant is saying where can it be shifted, or excuse me, where is it always going to kind of end up on, right? So maybe right now, because we heated it up, we've caused the reaction to shift to the product side or whatever the case is. That would be the temporary situation. And so that's kind of the idea of like, as soon as we open the mall, the equilibrium position was definitely shifted outside the mall. There was a lot more outside the mall than there was in. Now that position kind of shifts slightly as the mall's open, but as mentioned, the equilibrium constant for that scenario is always going to state that there's more people outside the mall. So an equilibrium constant is saying, given any circumstance, what is this reaction always going to be like? Are we always going to have more product or always going to have more reactant? The equilibrium, that was constant. I don't know if I said that was constant, right? The equilibrium position, whatever, it froze, but if it froze on my side, on your side, then whatever. The equilibrium position is basically the kind of now of the situation. Where are we right now, okay? The constant is where is it always going to be. So we looked at how to calculate that. It's always concentration of products over concentration of reactants. You only include gases and aqueous solutions. Why? Meh, I don't know. But it just is what it is. So the concentration of the product goes on top. If they have a coefficient, that's the exponent. Based on those of you who submitted that, it didn't look like there were a lot of issues, but go back and check. Especially with numbers 1E and 1G in section 2. Go back and check to make sure you didn't include liquids and solids, okay? So I'm going to pause. I'm going to go ahead and stop this video now because it looks like it froze, and if it did, well, then, that's not really going to be very helpful. But if it did not, well, then we continue to have this and we're set, okay? So if you have any questions at this point on this basic introduction to equilibrium, let me know. That's what we're going to kind of focus on for the next couple of days. And then we're going to next week start to shift into calculating, okay? Hope you guys are having a great week, and I will see you soon.